All right, so doing the math section from that 2005 ACT. So why don't you start by telling me which problems you want to go over? Did you get a chance to grade it already?
Yeah.
Cool. So where should we jump in?
16.
All right. What is the slope of any line parallel to this line in the standard coordinate plane? All right, so first of all, to answer this, we need to know what does parallel mean, right? What does parallel mean?
Like same slope, but different points.
Yeah, good. So two lines are parallel if they're going the same direction. And in terms of a graph, that's going to mean that they have the same slope. So the slope of any line parallel to this line will have the same slope as this line. So obviously, to answer that question, we need to know what is the slope of this line. How do we figure that out?
I kind of forgot about like equations for slopes. So
So I think the easiest way is to rearrange this equation into slope-intercept form. Y equals mx plus b. Because once you rearrange it to that, then whatever your m is, that's your slope.
Okay, yeah.
And
so
that would be
you'd get like negative 8x.
Right. So you're thinking start by subtracting 8x from both sides, right? So you get 9y equals negative 8x plus 3. And then what would you do next?
Divide by 9.
Right.
And then get you negative 8 over 9, right?
Right. And we don't really care what b is. It ends up being 3/9, which is 1/3, but that doesn't matter. We don't really need to get that. All we need is the slope.
Okay.
So that's our answer. Because yeah, it'll have the same slope. Any questions on that one?
No, that makes sense.
Okay, great.
And then my next one was 24.
All right. The lengths of the corresponding sides of two similar right triangles are in the ratio of 2 to 5. If the hypotenuse of the smaller triangle is 5 inches long, how many inches long is the hypotenuse of the larger triangle? All right, so I would start by just drawing two triangles. We know they're right triangles, so there's like a smaller one, and then there's a bigger one that is similar. What does it mean that triangles are similar?
Same angle measures and like the different side lengths.
Good. Yeah. So yeah, basically the same shape, different size is the way I like to think of it. Which means all of the corresponding sides are proportional, right? So in this case, the ratio is 2 to 5. So if, for example, this were 2 inches, we would know this were 5 inches. That would satisfy it. Okay, so we're given a length. We're given the hypotenuse of this triangle. The smaller one is 5. How many inches long is the hypotenuse of a larger triangle? So what do you think? What was your approach to try and figure that out?
I did it like you have the 2 to 5 ratio. So then I did 5 times 2 equals 10. And then I think it was, what was it? I think I did 5 times 5 equals like 25.
Yeah. So you're definitely in the right ballpark. I think the only mistake you made there was you multiplied by 2 instead of dividing by 2. So think about it this way. With the first example I gave with the 2 inches, right? If this is 2, this is 5, because when you divide by 2 and multiply by 5, you get to 5, right? So this 2 to 5 ratio here, you could think of it as a fraction. So we can get whatever this side length is, if it's 2, we multiply by 5 over 2, and that's going to give us the larger side length.
Oh, okay.
So the larger triangle is 5 halves the length of the smaller triangle. So that gives us 5 in that example. In this one, where the hypotenuse is starting at 5, multiply by 5 halves, and you get 25 halves, which is 12.5.
Okay.
Does that make sense?
Yeah, it makes more sense. Yeah.
Cool. So you could use proportions to set that up if that was a little easier for you to follow. So like you could say, so let's say we set up a proportion that was like small to large, right? So we know that proportion is 2 to 5. And we know that that is going to be the same proportion as the one we're looking for. So if this is x, then we can say that 2/5 has to be the same as 5 over x. So this is called a proportion, right? Whenever you have an equation that's like a fraction on both sides, it's a proportion. And solving that for x will give you that length.
So do you cross multiply, right?
So here you would cross multiply, which I kind of hate cross multiply because students like use that anytime they see fractions or a couple of fractions, they're always like cross multiply. But really it's a very narrow, you can only use it for proportions, which this is, so this is the right time to use it. But I kind of hate it. I always think instead of like, just use your normal rules for solving equations, which is we need to get x out of that denominator. So multiply both sides by x. And then we want to get rid of 2/5. So divide both sides by 2/5 or multiply both sides by 5 halves. So multiply both sides by x, you get 2/5 x equals 5. Divide both sides by 2/5 or multiply both sides by 5 halves. To cancel that, this goes away, and we end up with just x equals 5 times 5 halves, which is what we said earlier.
Okay, yeah.
Yeah. So again, I stay away. One of those cliches that like literally every math teacher teaches is the cross multiply, but I just think it's so easy for students to like that phrase sticks in students' heads better than like when they should be using it, and so they end up using it the wrong time. So I don't like to teach it at all. Especially because it's so narrow, it's only usable in one equation, and we already have tools to solve that equation. So I don't know why give students a special tool that is so narrowly useful when we already have perfectly good ones to solve that.
Yeah.
So that's my advice on cross multiply is just forget you ever learned it.
Okay.
All right. Yeah, where to next?
Uh, 26.
All right, in the circle shown below, M is the center and lies on line RU and line ST, which of the following statements is not true. All right, so 4 out of 5 of these are true. Why don't you tell me first what approach, how did you do this to begin with?
Oh, it was kind of taking me a long time, and I was kind of realizing how much time I had left. So I kind of just saw that TXU does not look like 50 degrees at all, and then chose that one.
Okay. So TXU here is the measure of an arc, right? This is this arc measure. And there's a theorem that says that the arc measure in a circle, the arc measure is always equal to the central angle that intercepts that arc. So this angle is the same as this arc. So if this is 50 degrees, which it is because of vertical angles, then this is also 50 degrees.
Okay.
So we know that one has to be true.
Okay.
RM is congruent to TM. That one obviously is true because those are both radiuses, radii. So we know that is true. RS and SM. Okay, so that's the one that doesn't have to be true. It could be true. We can't prove that it's not true, but we also Oh, you know what? Actually, we can prove it's not true. Because the only way that could be true is if this was an equilateral triangle. And this would only be an equilateral triangle if this were a 60-degree angle.
Oh, okay, yeah.
So that's not 60, so it's not equilateral. And since we know these two sides are the same, we know this side has to be different. So it's RS is definitely not the same as SM. So that's the one we're looking for. Let's talk real quick about the other two, just so we know why those are false. I mean, why those are true. Angle TUM, so that's this angle, measures 65 degrees. Okay, so that actually uses the same logic that I was just talking about. If we know this is 50, we know these two angles have to be the same because these two sides are the same. Do you get that part? That
Yeah, because the radiuses.
Right. But why is it that if these sides are the same, why do these angles have to be the same?
Because they share the line of TU, and then the lines, their radius lines are the same length, so they have to be angled the same way.
Yeah, okay, I think you're getting the right concept. What I'm going for here is the idea that this triangle is isosceles, right? And an isosceles triangle has two equal sides, and it also has two equal angles, the ones that are opposite those sides.
Yeah.
And this is not exact, this is a bit of a tangent here, but I do think it's useful if you have a triangle with three unequal sides. If you order those sides from smallest to biggest, so smallest, middle, and biggest side, the angles will be in the same order. So the opposite the smallest side is the smallest angle, opposite the middle side is the middle angle, and opposite the biggest side is the biggest angle, right? So they're kind of in order that way, or they're paired. And so if two of those sides are the same, you can kind of see the logic of, oh, well, then the sides opposite them would also be the same, and vice versa. Does that make sense?
Yeah.
And if all three sides are the same, then that means all three angles are the same too, kind of the same extended logic there. So that actually can come in handy occasionally on some of these problems. But the main thing for this one is because we know those two sides are the same, then we know those two angles are the same. So if the two angles are the same, how does that get us to 65 degrees? Can you explain that part?
Because 180 minus 50, and then is 130, and then that divided by 2 equals 65.
Right, and where's 180 coming from?
The sum of all three angles of a triangle.
Right, so in every triangle, they all are always 180, subtract 50 leaves you 130, divide by 2, and that's 65, great. Okay, so last one, TU is parallel to RS. TU is parallel to RS. Ooh, that's a tricky one. How do we know that's true?
Because is it just because like the angles are like, that the angles are the same?
Which angles?
Triangle?
Yes, it is that. Which angles are you talking about specifically are the same?
The 65-degree ones.
So it's not that these two in the same triangle are the same, it's that this angle is the same as this one.
Oh, okay.
So do you remember learning about parallel lines and transversals? Does that sound familiar at all?
Yeah.
What do you remember about them?
I remember that transversals, like the angles that correspond across I forget what a transversal is, I think, but
so the transversal is the line that crosses two other lines. So if we draw, let's use this color. So if we call ST a transversal across these other two lines,
okay,
then you can see that the blue angles that I highlighted earlier, those are what we would call alternate interior angles, right? And so they're interior because they're between the green lines, and they're alternate because one's above the red and one's below the red. So they're alternate interior angles. And if alternate interior angles are congruent, then we know the lines that they're cutting across are parallel. And that works both ways. So if we know the lines are parallel, then we know alternate interior are congruent. And if alternate interior are congruent, then we know the lines are parallel. So that's a both ways theorem. Yeah, so that's a little bit more obscure. It's easy to forget that one, but because those are the same, then we know those are parallel.
All right, yeah.
Does that seem familiar now that I've said it? The
Yeah,
alternate
I
interior.
remember the alternate exterior and alternate interior angles.
Yeah. While we're here, let's talk real quick about the rest of the parallel line stuff, because that could come up too. So you mentioned alternate interior, where I mentioned alternate interior, then you mentioned alternate exterior. What do you know about alternate exterior angles?
Would that be on like this question, like the angle next to the two blue angles you drew?
Mm-hmm. So you
And
mean,
they're congruent too.
so you mean like, we could say this angle and this angle are alternate exterior. Is that what you were saying?
Yeah, but then also the angle of the green and red line next to it too.
The one
Right.
below,
Yeah.
like, let's use this color. Just can need a bunch of colors here. So like this one and this one are also alternate exterior.
Yeah, and then the last one is across from the orange one.
Right,
Those
vertical
are
to it. And those two would be not alternate exterior, right? Those would be
Oh
alternate
yeah.
interior. Right, so yeah, so all of those pairs we just mentioned are congruent. And in fact, all of the orange angles then are congruent, and all the blue angles are congruent as well. So what do you call, like, let's say I'm talking about this blue angle and this orange one. What would we call those? Those are not alternate interior. They have a different name because they're both above the red line.
Which ones?
So this angle and this one.
Okay. They're, I know that they add up to equal 180.
Yes, good. So they're supplementary.
Oh yeah.
Yep. And they're called same side interior. So not alternate, alternate being on different sides, same side on the same side. Yeah, and so they are supplementary. So what that tells us then is any of these blue-orange pairs are always supplementary. So like these two are a linear pair, so you know they're supplementary. Same thing here, but then you can go across to same side interior, those are supplementary, or same side exterior are also supplementary. So any pair of angles that you pick on two parallel lines and a transversal, they're always either congruent or supplementary, depending on which pair you pick. And again, all of these theorems work both ways. So if you know they're parallel, then you know that they're either congruent or supplementary. And if you know they're congruent or supplementary, then you know that's parallel. Right? So all of those things go both ways. So if you're trying to prove things parallel, you can go one way. If you already know they're parallel and you're trying to know something about the angles, then use in that direction.
All right, yeah, that makes sense.
Great. All right, cool. Quick little parallel review there. Any questions about any of that?
No, I don't think so.
Cool.
Yeah. My next one was 37.
What is the maximum number of distinct diagonals that can be drawn in the hexagon shown below? All right, tell me what you did to give this one a shot.
So I knew that there was like a theorem that you can do, but I kind of forgot the theorem.
Yeah.
So I just tried drawing it in and I got 6.
Okay. So let's see how many we can come up with now. So I would start with one angle and then work my way around. So if I start with this vertex here and draw diagonals, you can draw 3 diagonals from that vertex.
Oh, okay. I think I missed the first one you drew.
Gotcha. Yeah, a diagonal is any line that connects one vertex to another vertex that isn't a side. So
Oh, okay.
triangles don't have any diagonals. Quadrilaterals have two, and so on. So we'll come back to that theorem that you mentioned in a second. But let's keep going around. So the next one, so let's go to the next vertex and draw all of the diagonals there. So you get 1, 2, 3 more. So let's write some down here. So we've got 3, and then 3 more, and then let's keep going around. So now we come to this vertex, but we don't have 3 to draw now. So this is where the first thing changes, because now one of the diagonals is already drawn. So we only get 2 new diagonals. So we'll put a 2. And then if we keep going around to the next vertex, now 2 of those diagonals are already drawn. 1, 2, and so there's only 1 new one left to draw. And from that pattern, you might guess what's going to happen at the next one. So if we go to the next vertex, now all 3 are already drawn. So we have no new diagonals from there, and the same thing at the last vertex. All 3 are already drawn. So we get 3, 3, 2, 1, add all that up, and that's 9 diagonals that we can draw.
Yeah, I think I missed those ones that you drew, like
the ones that are straight
down, kind of, because
they don't look diagonal.
Yeah.
So one thing to be careful of in general is trying to, there's some words that are like, have really specific meanings in math, particularly in geometry, but kind of across the board in math. There's words that have really specific definitions, but those words are also used in like common everyday English and have very sometimes closely related definitions, but usually not the exact same definition. So diagonal is a great example of that, because normally in day-to-day conversation, when we say diagonal, we mean slanted, right, at an angle, or not straight up and down. Yeah. But in math, that's not what it means, even though there is, it's related, right? Because if you draw a rectangle and you put the diagonals in there, the diagonals are slanted. And I think that's how that kind of definition crossed over. Actually, I don't know. I'm not a linguist. I don't know which direction which definition came first. But so diagonals in a right kind of straight up and down quadrilateral, they are slanted, but they don't have to be. So there's a lot of examples of when a math word and is kind of the same word in everyday English, but is not the same, doesn't have the same definition. So just be careful of those, I guess. I'll point them out as we come across them.
All right.
Diagonal is definitely one. Maximum is one that actually does use the same definition in math that we use every day. So that's an interesting counter example. Anyway, the answer here is 9. And that's all there is about that one. Any questions or thoughts?
What is the theorem for it?
Oh, right. So all right. So I already said in a triangle, there are no diagonals, right? So in a triangle, there are 0 diagonals. In a quadrilateral, right? So in a rectangle, there's 2 diagonals. In a pentagon, let's draw a pentagon. So draw a simple little pentagon and see how many diagonals we come up with. So we would get 1, 2, 3, 4. That one's already drawn. 5, and the rest are already drawn. So we get 5 in a pentagon. In the hexagon we just did, we get 9. So you can kind of see the pattern here starting to form. It's +2, +3, +4. So let me actually, I'm not sure I remember exactly what. Let me Google this theorem. Polygon diagonal formula. N times n minus 3 over 2. All right, so the formula is, if you wanted to take a shortcut, it's n times n minus 3 over 2. So notice this is a quadratic formula, right? Because it's n times n. So there's an n squared, which matches kind of what we'd expect based on the way this pattern is. But let's plug it in. So if you plug in 3, it'd be 3 times 3 minus 3. So that's 0 over 2. So that's 0. Plug in 4, you get 4 times 4 minus 3. So that's 4 times 1. That's 4 over 2. That's 2. So that works. Plug in 5. 5 times 5 minus 3. That's 10 over 2 is 5. One more, plug in 6. 6 times 6 minus 3. That's 18 over 2 is 9.
All right, yeah.
So anyway, that's the formula. I would not really expect you to remember that. It's a pretty random one, really specific, but that is the Polygon diagonal formula. It's probably easier to just do a little pattern and start to figure out how that goes and then count up, a lot like the blocks problem we started with, rather than trying to memorize that.
Yeah. So I realized that 33 I got right on, but I kind of like guessed on it. So I think we should go over that one.
33.
Yeah.
Okay. In the figure below, ABCD is a square. Points are chosen on each pair of adjacent sides of ABCD to form 4 congruent right triangles. And you remember what congruent means?
Yeah.
Can you explain it?
Like their side lengths are the same, their angles are the same.
Good, yeah, same shape, same size. As shown below, each of these has one leg that is twice as long as the other leg. Okay, so let's, if this side, oh, actually they have it already shown right here. They have x and 2x. Great, so we could go around and label that all the way around if we wanted to. Each of those, blah, 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 blah. What fraction of the area of square ABCD is shaded? Okay. Trixie. How do we get started on that?
Do we know that it's a 30, 60, 90 triangle?
We don't. In fact, we know that it is not a 30, 60, 90 triangle.
All right.
Let me show you how I know that. So in a 30, 60, 90 triangle, whatever length the shortest leg is, it's exactly half the length of the hypotenuse. And the long leg is that same length times the square root of 3.
Oh, okay.
So this is similar. It kind of reminds us of that because of the 2x, but it's in the wrong place.
Mm-hmm.
So it's definitely not 3690. Okay, so what else can we do to try to figure this out?
You do Pythag?
Yeah, we could do that. So if we do Pythagorean theorem, we could say x squared plus 2x squared is the hypotenuse squared, or c squared, I guess. So that's x squared plus 4x squared is c squared. So that's 5x squared is c squared. Take the square root of both sides, and you get the square root of 5x equals c. So that missing length is the square root of 5 times x. Okay, so we know the missing side lengths. How is that helpful?
You can do that square to get the area of the square.
Good, and we know what that squared is. We just did that, so that's 5x squared, right? So that the gray area has an area of 5x squared. Awesome. Okay, so that's definitely feels like a step in the right direction. What else do we need to know to answer the question?
like how much isn't shaded? So
Yeah, we could do that. Actually, that's going to be a little harder and a little more indirect. Then what we really need to know is what is the area of the entire square,
oh yeah.
right? Because the question is what fraction of the entire square is shaded.
Mhm.
So if we know the, in other words, we want to know the answer we're looking for is the shaded area divided by the whole area. That's the fraction we're looking for.
Okay.
So we just found out the shaded area. So now if we just know the whole area, then we'll be done.
And you would do 2x plus x equals 3x, then 3x squared,
Exactly. And what is 3x squared?
9x squared. So then you cancel out the x squared, right?
Perfect. X squared goes away and you're left with 5/9. So 5x squared is shaded, 9x squared is not shaded, so that's 5/9 of the whole thing is shaded.
Oh yeah.
Like I said, we could have done that by what you were starting to do is you could add up all the areas of those white triangles. That would get you there, but then you'd end up having to sort of add it in anyways, right? So you would end up getting 4x squared. You would add that to the 5x squared, get 9x squared, and you'd do this fraction anyways. So it's just extra steps for no reason.
Mhm.
So yeah, the better solution is just to find the whole thing.
All right. Yeah, that makes sense.
All right, cool.
My next one was 38. Yeah.
All right, in the standard XY coordinate plane, the center of the circle shown below lies on the axis at x equals 4. Sorry, we're getting rid of lines. The center of the circle shows the x-axis at x equals 4. If the circle is tangent to the y-axis, which of the following is an equation of the circle? Oh boy, okay. So this is a problem that's pretty easy if you remember the equation of the circle, and pretty hard, maybe impossible if you don't.
Yeah.
So there's not a lot of equations that I really recommend memorizing for the SAT, ACT, but this is one that I think is worth memorizing. So let's write it down. Equation of a circle. All right, do you remember off the top of your head? Actually, this is a big hint. This looks a lot like it. Do you remember what the equation of a circle is?
It's pi r squared, right?
That's the area of a circle. Yeah,
Oh.
but I'm looking for the equation that describes a circle when you graph it, the XY equation. So
No, I don't remember.
so it's x minus h squared. Is it looking familiar yet?
Kinda.
Y minus k squared equals r squared. So that's the equation. In this equation, the point HK is the center and R is the radius.
Mhm.
So let's think about in our circle here, what is the center? What's the coordinates of the center?
4, 0.
Right. 4, 0 is the center, and then what's the radius?
2. Right now. 4.
Yeah, good. So our radius is this length, or I guess easier to find this length, which we know that's 4, and then the center is 4, 0. So let's plug that into this equation. Go ahead.
So you know it equals 16 at the end, and then it would be minus 4. So then,
Yeah, so it'll be x minus 4.
and then plus y squared.
Y, right. Why just y squared? What's k?
0.
Right, so y plus 0, which means we can just drop it, so it just ends up being y squared. Great. So there's our equation. So that is what?
G.
All right. Is that do you think you'll be able to remember that formula?
I think so.
It might be worth like writing down once or
Yeah.
twice, or writing on a flashcard, or just write it down somewhere, maybe a couple times, see if you can get it stuck in your head. I don't think it's too hard. And actually, what's interesting about it, do you remember, do you know the distance formula off the top of your head?
No. Actually, kind of, I think.
Do your best shot. It's very similar to this one.
Yeah, isn't it like x? Is it the same thing except without the squared?
It actually does have the squared. So it's normally written as x2 minus x1 squared plus y2 minus y1 squared equals the distance squared. Shrink that a little bit. Fits in there. Okay, do you see how similar that is to the equation of the circle?
Yeah.
Do you have any idea why that might be? Why is that so similar? Do you think it's a coincidence, or do you think, I mean, I guess because I'm asking the question, you probably know it's not a coincidence.
Yeah. I don't know. I'm not sure. Yeah.
Do you know what the definition of a circle is?
No.
So a circle is the collection of points that are all equidistant from the center. Right.
Okay.
So in other words, if you start with a point and take a string that's 4 inches long and draw a line that is all of those points that are 4 inches from the center, you'll get a circle. So that's the definition. But think about what I just said. They're a collection of points that are equidistant. So distance is in the definition of a circle. So that's why the distance formula is so similar to the equation of circle, because a circle is defined by distance. So this is all of these points, x, y points, that are the same distance from HK.
Oh, okay.
Does that make sense?
Yeah.
And let's go one step further. What other formula kind of looks like these two? Not as similar, but has a similar structure.
Pythag.
Yeah, the Pythagorean theorem. So the Pythagorean theorem is obviously a squared plus b squared is c squared. So why do you think that is so similar?
Because obviously like the squareds are the same. I don't know what makes it like the same other than that.
So let's look over this graph. Just draw a point on the graph, 2 points. So we got 2 points, and I want to know how far apart those 2 points are.
Oh, yeah.
The way you figure out how far apart those 2 points are, obviously you can use the distance formula, but like geometrically, what we're going to do is construct a right triangle. Right, we're going to draw a line here and a line here. And that makes a right triangle. And the sides of that right triangle are just so the bottom of that right triangle is x2 minus x1. That distance is the bottom of the triangle, and y2 minus y1 is the vertical side of the triangle. So y2 minus y1 is A, x2 minus x1 is B, and the hypotenuse is C. And so the distance formula is just the Pythagorean theorem, which then goes on to define the equation of a circle. So I tell you all that one, because I think it's interesting, but two, because I also think it might help you remember the equation of a circle and the distance formula, which is another one that's useful to remember. So if you remember that both of those are really just the Pythagorean theorem, where you're just comparing those y values and those x values to get your a and b, then it all makes sense. It all fits together and might be a little easier to remember that way.
Oh yeah, okay.
Questions on that?
No, that makes sense, yeah.
All right, cool. So about out of time, we can maybe do one more. Where do you want to go next?
43, I think. Yeah.
All right. A local dealership is having an end of the model year clearance sale. It's a lot of hyphens in there. And is offering 5% annual interest on new car loans for 36, 48, or 60 months. A lot of information here. Max amount Kaylee can budget for her monthly car payment is $300. And the following loan amounts, which one is the maximum Kaylee can borrow at 5% annual interest and stay within her budget? Okay, that is a ton of interest, a ton of information that we have to sift through. How do we even start this?
So I got, I'm not sure. I kind of, yeah, I don't know.
So I'm going to start right in the middle with that 36, 48, or 60 months, because I think we need to know which one of those we're going to be working with.
Yeah.
If you want to get your monthly payments as low as possible, should you take a shorter loan or a longer loan?
The longer loan.
That's right. So if you give yourself the longest amount of time to pay it back, your monthly payments will be lower. You'll end up paying more total by the end of the loan, but you'll pay less per month. So we're going to take the 60-month loan, which is 5 years, right? 60 divided by 12 is 5. So 5% annual interest. How do we want to do this? So if we start with,
you can see that like you have 5% on the graph above. So you know that you get 18.87.
Oh my gosh, this has a this makes this so much easier. I was trying to like, okay, great.
I realized that there was a table thing.
Yeah, that helps so much. Okay, monthly payment per $1,000 borrowed. So if we want to go to 60 months and 5% interest, it's going to be $18.87 per $1,000. Right, so that actually makes this way easier than I was going to like try to come up with an equation for us to solve, and it was going to be a mess. This is much better. So we basically know we're going to be paying $18.87 per month per 1,000. So if we just say $300 divided by $18.87, that means we can pay 15.89. We can pay $18.87 a month 15.89 times before we hit our $300 budget. So at 16 times, so if we are paying $18.87 16 times, 1887 times 16, that is 301.92, which is just a bit over budget. And if we do 1887 15 times, then we get 283. So that's below our budget. So we can afford to pay this much. So that is 15 times this amount. And that amount equates to $1,000. So that's $15,000. If we borrow $15,000, we'll be paying $18.87 a month 15 times, which is $283.05, which is
Okay.
the max we can hit and stay under budget.
Okay, yeah.
Does that sort of make sense?
Yeah, it makes sense. Yeah.
All right. Any questions on how I got there?
I don't think so.
All right.